Hi science friends! Today we are talking about properties of solutions. So we talked about solutions a little bit in our last lesson. We also talked about colloids and suspensions and emulsions. So remember, emulsions are homogeneous like mayonnaise that's held together by an emulsifying agent, so it's the same throughout. Solutions are generally homogeneous, also being the same throughout. Colloids like Cool Whip are the same throughout. But now suspensions like that Italian salad dressing, if you go back to the other day's lesson, are heterogeneous mixtures. Those are different throughout. You see the kind of flakes of the Italian dressing float to the bottom and the oil kind of, or float to the top and the oil kind of sinks to the bottom. So solutions are homogeneous mixtures that may be solid, liquid, or gas. So usually when we think of solutions, we typically think of aqueous solutions. But gases can also be solutions too, like the air that we breathe. It's a homogeneous mixture of oxygen and nitrogen and different compounds or different elements. So let's talk about factors, that affect solvation. If you remember that term solvation, that's the ability of something to dissolve in. Okay, so factors that affect dissolving, if that's an easier term for you, even though dissolving is not really the correct way to say it in that sentence, that's what it means. How something dissolves, that's solvation. So the first one is the nature of the solute and the solvent. And so what I really want you to remember, I know that you all don't have notes for these today. I apologize. You may want to jot down some notes on a piece of paper, or I will post them in the PDF in Google Classroom if you have a way to be able to print that out at home. But like dissolves like, okay? What that means is polar molecules will generally dissolve other polar molecules. Non-polar molecules will generally dissolve other non-polar molecules. So you can mix non-polar and non-polar, you can mix polar and polar, but what you can't mix is non-polar and polar, okay? Because like dissolves like. And so when we're looking at the solvent and we're looking at the solute, we want to look at those properties, and that's going to determine how well they dissolve in one another. So these factors, what I want you to know about these factors is it affects the rate, okay? All of these other factors don't determine whether it's going to dissolve, but it's going to, maybe I should just put these in here. It's going to affect the rate of solvation. So for example, stirring. Stirring increases the rate of solvation. You can stir oil and water until your arm falls off, but that will not make it dissolve. So if it's not going to dissolve, stirring is not going to help it. And so that's why I'm kind of highlighting these here and saying it doesn't affect whether it's going to dissolve, but it's just going to affect the rate at which it does, at which it will. If you've ever made tea before, a pitcher of tea, you always stir the sugar in at the end, right? Like eventually that sugar will mix up and incorporate into the tea. But if you're going to pour your glass of tea right away, you want to stir it up first to make that happen faster. So it affects the rate. Okay, temperature is another one of those factors. So increasing the temperature increases the rate of solvation. Remember, temperature is a measure of kinetic energy. These particles are always in motion. And so when you increase the temperature, those particles are moving around faster. And so when they're moving around faster, they're more likely to dissolve one another. Okay? And they're going to dissolve one another faster. And then the last one is particle size. So particle size, if you decrease the particle size, that should say increases the rate of solvation. Decreasing the particle size is going to increase the rate of solvation. So smaller molecules are going to, or smaller compounds are going to dissolve faster. That's why when you put sugar in your tea, if you put granulated sugar like table sugar, which is what we probably all use, it's going to dissolve a lot faster than, say, a sugar cube, okay? Because it's a smaller molecule, and the particle size is going to increase the rate of solvation, okay? So when we talk about solubility, we talk about our solutions, and solutions may be saturated or unsaturated. And so what that means is saturated solution contains the maximum amount of solute that a given solvent can hold at a certain temperature. Okay, so let's say if you were going to stir, if you take a thing of water and you are going to stir salt in it. Okay, your water's at room temperature, it's at 25 degrees Celsius, and you're going to add salt. There is only so much salt that water can hold. Okay, you can't keep adding cup after cup of salt and it keep absorbing it. And so when it holds the maximum amount, then it's considered to be a saturated solution. Okay, now if you increase the temperature, you can increase the solubility a little bit. So for example, for 100 grams of water at 25 degrees Celsius, it will only hold 36.2 grams of salt. Okay, that's all it'll hold, 36.2 grams of NaCl. But if you bump the temperature up a little bit, then you can get a little bit more in. Okay, and so this term, this 36.2 grams of salt per 100 grams of water, is called its solubility, the amount that dissolves in a given quantity of solvent at a given temperature to produce a saturated solution. And as we just said, it's generally expressed as numbers of grams per 100 grams of solvent. Okay, so anything that is not saturated, that doesn't have the maximum that it will hold, is considered to be unsaturated. So if 36.2 grams is saturated, if you have 36.1 grams, that's considered unsaturated. Okay, or if you have 4 grams, it's considered unsaturated. But anything less than saturation is considered to be unsaturated. Okay, now liquids that will dissolve in each other are considered to be miscible. Liquids that do not dissolve in one another or that are insoluble, such as oil and water, those are considered to be immiscible. Okay, an example here is like water and alcohol. I mean, like isopropyl alcohol, rubbing alcohol. You can dissolve that. Hydrogen peroxide is another good example. So when you buy hydrogen peroxide at the store, it's 6% hydrogen peroxide. So that means if you make up 100 milliliters of hydrogen peroxide, 94 milliliters is actually water, and the other 6% is pure hydrogen peroxide. Okay, H2O2. So those would be considered miscible if they mix in. Now, factors affecting solubility. As we just said, solubility of most substance increases as the temperature of the solvent increases. So we said for 100 at 25 degrees Celsius, 100 grams of water will hold 36.2 grams. But if you go to 400 degrees Celsius, then you can get 39.2 grams. So you have to get quite a bit up higher to add a little bit more. Okay. I think that was the right 400 degrees Celsius. I could have made that up. I don't know where I got that number from. So what we look at here, this is referred to as a solubility curve. And so a solubility curve will show us lots of different salts. So remember, a salt is just an ionic compound. It's a metal and a non-metal. So when we think of salt, we usually think of table salt, which is sodium chloride, NaCl. But a salt in chemistry is any ionic compound, a cation and an anion, a metal and a non-metal. So here we have sodium nitrate. That is a salt, okay? So we see that at 0 degrees Celsius, that you can put about, 73 grams of salt, of sodium nitrate in 100 grams of water. But if you jump up to 35 degrees Celsius, from 0 to 35, then you'll get 100 grams of sodium nitrate into 100 grams of water. Okay, and so this is a solubility curve, and that's how you read it. So you see lots of different compounds on here. You can read it for lots of different compounds. Now, gas is an exception to this rule. We say that the solubility of most substance increases as the temperature of the solvent increases. But that is not true for gases, and we'll come back to that in just a second. Namely, right here. Okay? So for gases have increased solubility in cold water than in hot water. And so this is why fish generally like to live a little bit deeper in the ocean. If you go deeper in the ocean, the water's a little bit cooler. And so it holds more oxygen. The water has more oxygen in it. It is more saturated with oxygen down a little bit lower where the water temperature is a little bit cooler. Some power plants and different industries, they will often pump water out of a river or a lake or an ocean and run it to their facility and then recycle it back into the lake. And when they do that, it's really harmful for the fish and the plants living in that area. It's called thermal pollution because it really changes the temperature dynamic and affects the quality of the water. For one, the quality of the water, but also the saturation of the oxygen levels and the carbon dioxide levels in the water. And that can definitely have a negative impact on the fish. Okay. Also, gas solubility increases as the partial pressure of that gas increases. So this is really evident in, I'm going to write fish here. Maybe you want to write fish there so you can remember that. Fish in the ocean. Okay. Colder equals more oxygen. So fish live deeper. Okay. Here I'm going to write carbonated beverages. Isn't it cool how chemistry is like all around us? We just don't think about it. So carbonated beverages are a great example of solubility and pressure. So when you first open a Coke, like a 2-liter bottle or a 20-ounce bottle, it is under high pressure. You open that top and you hear the psh, as it releases that gas pressure from bottling, or if it's been shaken up, right? If you drop it or you shake your Coke up really hard, when you open it up, it may even spew out on you, right? Because when it's been shaken, those molecules are colliding with one another. And if you think back to our gas law unit, that also increases the pressure. And so when you open it, it's very bubbly. But now think about the difference. What if you leave the lid off of your Coke and leave it out on the counter overnight? When you go to drink it the next day, what's your Coke like? It's flat, right? The CO2 actually dissolves out of the solution. So in your Coke is dissolved carbonation. It's CO2 bubbles are in that solution. That's why it's called a carbonated drink, right? CO2 is the carbonation. And so if you release that out, if you decrease the partial pressure by opening the lid, then you release those bubbles. Those bubbles will be released out of solution. They're not packed in there in that headspace above the liquid anymore. And so the gas solubility is going to increase when it's under pressure, decrease when it's under less pressure. Okay, so that's why carbonated beverages, I'm going to make a little note here that you may want to write down too, are fizzy when first opened because there's lots of pressure. If you leave the top off, the CO2 is left. No more, I think I didn't really do a good in there. CO2. So there's less pressure because you don't have a lid to hold that pressure in. And so there's no fizz anymore. And it's flat. Okay, so hopefully if you make notes to yourself like that and you kind of think about it like that, it helps make sense of it all. All right. So we have one little calculation to do here, and you'll have a worksheet on this today. And then as well as on those solubility rules, you'll have to just do those on your paper because you don't have the assignment. I had no idea that we would end up being out of school for so many days in a row when I saw you all last week. So Henry's Law. Henry's Law tells us at a given temperature, the solubility of a gas in a liquid is directly proportional to the pressure of the gas above the liquid, okay? And that goes back to what we're saying here. If we increase the pressure, it's going to increase the solubility. So keep in mind that when you're getting your answers. If you increase the pressure, your solubility number should increase as well. So our equation here is S1 over P1, solubility over pressure, equals S2 over P2. So let's look at this first problem. If the solubility of a gas in water is 0.77, so that's going to be my first S1 over P1 equals S2 over P2. So that's my first solubility, okay, grams per liter at 3.5 atms of pressure. What is its solubility? So that's what we're solving for in grams per liter at 1 atm of pressure. Okay, now it is possible that I could give you some that have different pressure units. Those both have atms, so we're good here. You don't have to convert between pressures, but if we do, you know how to do that. You may need to pull out that gas laws paper half sheet that I gave you to remember those conversion factors, but you would know how to do that. So we're going to solve for this. Now, we should expect our number to decrease. It should be less than 0.77 because when our pressure decreases, when our pressure decreases, the solubility decreases. So if we do this here, 0.77 times 1, I'm going to cross multiply, and then I'll divide by 3.5. So I should get, remember 0.77 times 1, so that would be 0.77 atm grams per liters equals S2 times 3.5 atm. I think y'all know how to do that mathematically, but that's how you would do it. And then we're just going to divide both sides by 3.5 atm. Well, our atms will cancel out, and it leaves you with 0.22 grams per liter equals S2. And as we said, that decreased, right? Our pressure went down, and so our solubility should have also gone down. So I'm going to give you one to try here. I'm going to pause, and then you can work it, and then we'll come back and take a look at it together. So on this one, you should have gotten 0.44 grams per liter, okay? And again, the temperature has to remain constant on these because remember, if the temperature changes, that changes the solubility. Increasing the temperature is going to increase the solubility. So we're not going to include that factor in here. So we're going to leave the temperature constant and see what's going to happen to the pressure, okay? Last slide for today. So we talked about saturated solutions when it has the maximum amount of solute that the solvent can hold. Unsaturated solutions is even less than that. So the last thing though I want to talk about is a supersaturated solution. And so a supersaturated solution is when you can get just a little bit more solute in there than what it should technically hold. And so the way that you do that is you take a solution that is saturated, and you raise the temperature up on it and you add a little bit more solute, okay? And so then it's still saturated at that new higher temperature. But then if you slowly, very slowly, drop the temperature back down, sometimes you won't cause the solution or the solute to precipitate out. It will stay mixed in the solution. And in that case, the solution is considered to be supersaturated. It's holding technically more than it should for that temperature, okay? So you take a saturated solution, heat it up just a little bit, add a little bit more solute so it's saturated at the higher temperature, but then very slowly drop it back down, okay? And so then it's considered to be super saturated. So an unsaturated solution, you have more solute dissolves in the water. You can have more and more that's added